Watch this tracer circle the hub. Its distance from the center stays fixed. The turning rate readout stays fixed. Even its speed stays perfectly fixed. So is its acceleration 0? Look at the velocity arrow, not merely its length. Sample that arrow at equal times. Every copy has the same length, yet every copy points in a new direction. Bring the arrow copies to one starting point. Their tip-to-tip change points inward. Acceleration is here. But if scalar readouts look steady, where is that inward change hiding? Motion around a center suggests better measurements. How far out and how far around? Keep the origin fixed in an inertial plane. Call the outward distance the scalar r and the counterclockwise angle phi. Attach a compass to the tracer. The plane stays inertial, only these directions rotate. R hat has unit length and points outward. Phi hat is perpendicular toward increasing phi. Keep r positive because outward is undefined at origin. The bold position vector differs from scalar r and unit r hat. It begins at the fixed origin and reaches the tracer, so position is r times r hat. A dot means change per second. 2 dots mean that rate changes. Measure phi in radians. A small turn delta phi sweeps arc length r delta phi. On a unit circle, arc length itself equals delta phi. Now compare r hat before and after one small positive turn. Both arrows still have length 1, only their direction changes, so place the two copies at a common tail. The arrow from the old tip to the new tip is the change in r hat. It leans toward phi hat. Divide by elapsed time, then shrink the time and the turn. The difference arrow settles along phi hat, while its size per second becomes phi-dot. Therefore, r hat changes at rate phi-dot along phi hat. Unit length never meant a constant direction. Repeat the same experiment for phi hat. At phi equals 0, it points upward. After a small positive turn, the new copy tips slightly left. Its tip-to-tip change points inward, opposite r hat. As the turn shrinks, its magnitude per second again approaches phi-dot. Phi hat changes as negative phi-dot r hat. We can rebuild motion one control at a time. First, lock phi and change only r. The tracer slides along a rail. Its in or out speed is r dot meters per second, directed along r hat. Next, lock r and turn only the angle. The tracer travels arc r delta phi. Divide by time. Sideways speed along phi hat is r phi dot. Radians per second times meters gives meters per second. Release both controls. The tracer can slide outward while the rail turns beneath it. Add the radial arrow to the transverse arrow tip to tail. Their resultant now follows the tracer's actual path. The calculus should describe that same picture. Differentiate position, r times r hat. The product can change because its length r changes and because its direction r hat turns. Use the two changes once each. Velocity is r dot r hat plus r phi dot phi hat. Now comes the real puzzle. Velocity has two component arrows and neither lives on a fixed compass. Each can change in length, direction, or both. Track those causes separately. Start with the radial velocity, r dot r hat. Freeze the compass direction and let r dot change. The arrow grows or shrinks along r hat, contributing r double dot r hat. Reset the arrow, keep its radial speed, and rotate the compass. Even with constant r dot, the arrow turns. Its change points along phi hat, and the turning rule gives magnitude r dot phi dot. So the radial velocity contributes r double dot along r hat, plus r dot phi dot along phi hat because its direction rotates. Turn now to the transverse velocity, r phi-dot phi-hat. Hold the radius fixed, but let phi-dot increase. The tracer sweeps angle faster, so the sideways arrow lengthens. That change contributes r phi-double-dot along phi-hat. Nothing radial changed, only the turn rate accelerated. Reset again. This time keep phi-dot steady while the tracer slides outward. The same radians per second now sweep a longer arc each second. Speed along phi-hat rises by r-dot phi-dot, producing another contribution along phi-hat. The compass is turning at exactly the same rate. There is one more change hidden in the transverse arrow. Its direction rotates. Hold its length steady and compare nearby copies. The tip-to-tip difference points inward. That is exactly the rule for phi-hat changing toward negative r-hat. Multiply that directional change by the transverse speed already present, r phi-dot. No speed readout had to change. Now substitute the rotating direction rule. The transverse speed already contains one factor phi-dot. Turning phi-hat contributes another. Together they make r phi-dot squared, and the minus sign places that acceleration inward, opposite r-hat. The transverse velocity therefore contributes 2 sideways magnitude changes and 1 inward direction change. Leave all 3 sources visible before combining anything. The radial velocity arrow rotates, creating the first mixed contribution along phi-hat. Growing radius raises speed along phi-hat, creating the same mixed contribution. 2 equal terms, 2 different causes. Move them together. Only now may the ledger write the factor 2. Now collect by direction, without losing the history. Along r-hat, the changing radial speed gives r-double-dot outward, while the turning transverse arrow gives minus r phi-dot squared inward. Along phi-hat, changing the turn rate gives r phi-double-dot. The rotating radial velocity and the growing transverse speed each give r-dot phi-dot, so together they give twice r-dot phi-dot. The acceleration vector is therefore r-double-dot minus r phi-dot squared, along r-hat, plus r phi-double-dot plus 2 r-dot phi-dot, along phi-hat. Every term now has one visible motion that earned its place. Test the result. Lock phi and change only the in-out speed. The compass does not turn, so only r-double-dot survives along fixed r-hat. Lock radius and turn at constant rate. Both second derivatives vanish, yet minus r phi-dot squared remains, pointing inward as the opening arrows predicted. Keep radius fixed but increase turn rate. The r phi-double-dot term points sideways, while the existing turn rate still demands the inward squared term. Finally spiral outward at steady radial and angular rates. Both mixed sources point along phi-hat, reverse radial motion, and both reverse while the inward term does not. For a constant mass particle, return to net force equals mass times acceleration. The law is unchanged, only our measuring compass moves. Read that net force vector along the live compass. Add every real force component along outward r-hat. Separately add every component along increasing phi-hat. These are signed components of the same physical forces, not forces created by coordinates. Now match like directions. The radial force sum equals mass times r-double-dot minus r phi-dot squared. The transverse, or phi, force sum equals mass times r phi-double-dot plus twice r-dot phi-dot. This second line is a force component equation, not a torque equation. Return to the opening circle. Fixed radius makes r-dot and r-double-dot 0. Constant turn rate makes phi-double-dot 0, while phi-dot stays non-zero. Substitute each fact in order. Inward remains. Radial force sum is negative mr phi-dot squared. The sideways force sum is 0. That is the hidden change. Centripetal force is not extra. It names the inward net result. Next, attach this compass to a skateboard in a half-pipe, which real forces supply the inward and transverse requirements.